In this video, I want to take a look at a somewhat obscure corner of the Haskell language and give the full story on two concepts, the defaulting concept that we have already been mentioning, and another somewhat related concept that is called the monomorphism restriction. And while you don't get into contact with this very often while programming in Haskell, it is nevertheless a source of potential confusion, and I think it's perhaps worthwhile explaining what's going on. So let's start with the following example. We have been seeing the bounded class, and the bounded class had two methods, minbound and maxbound, and they're both of type A. They're simply constants of type A, but the A is constrained to be in the bounded class. So if I actually ask for the type of minbound, then I get this A with the bounded A constraint. Okay. So I could decide that I want to give a different name to minbound for my particular application, that I would like to call it minimal rather than minbound. So I could decide that I want to make a binding in my module that says minimal equals minbound. Now all of a sudden I get an error message, and I get a strange inferred type here, which mentions a type called any. And what's the error message? The error message actually says ambiguous type variable arising from a use of minbound prevents the constraint bounded A from being solved. Now we've seen this error message about ambiguous type variables before. It happens if we are in a situation where we do not have sufficient contextual information in order to make a choice. And that's true. If we actually want to evaluate minbound at a concrete type, then which type do we choose? Like, do we want the minbound of the type int? Do we want the minbound of the type bool? But here we are making a binding to a new identifier. So why wouldn't GHCi just give it the type with the constraint again? And if we try this, we see that it actually works. So even though there is a perfectly valid inferred type for this expression, GHCi somehow refused to infer it in this particular instance, and instead triggered an error message about an ambiguous type variable. Okay, so that is strange. And we can observe a similar error message if we write the following function. Let's write a function equal to itself. That's a little bit of a contrived function. And I'm going to write it using a lambda abstraction. So I'm going to say equal to itself is the function that takes an x and checks whether x is equal to itself. And suddenly we see the same thing happening. We see that we get here a suggested type that involves this any, and we get an error message about an ambiguous type variable arising from an EQ constraint. And of course, the EQ constraint comes from the equality test here. But once again, if we ask for the type of lambda x equals x, we get that it has the type A to bool, where A is constrained via the EQ class. So why doesn't GHCi give this type? So again, we could say, let's give a type signature EQA A to bool, and this type is accepted. Okay, so this is strange. And it's even more fascinating because if we write equal to itself in the perhaps more natural style where the function argument is on the left-hand side of the equals, and we do not use a lambda abstraction, then GHC suddenly is perfectly happy of inferring this type that we want and is not giving an error message. Even if we do not have a type signature here, it's not giving an error message at all. And now we get a warning about a top-level binding with no type signature, but the type signature that is suggested is the right one. And if we ask now, what is the type as far as we are concerned that this function has, we get exactly the right type. So something really strange is going on here. And the strange thing that is going on here is a concept in Haskell that is called the monomorphism restriction. Now, the monomorphism restriction applies to top-level bindings that look like they are having no arguments. And what does it mean for looking like they have no arguments? It means they syntactically have to look like that. So syntactically, it has to be a binding of an identifier itself without any arguments to the left of the equal symbol. Right, so minimal is such a top-level binding without arguments. Equal to itself is a top-level binding without arguments, because even though it is bound to a function, that function appears completely to the right of the equals. And that is the big difference between equal to itself and equal to itself prime. That equal to itself syntactically looks like it has no arguments, whereas equal to itself prime syntactically looks like it does have arguments. So the monomorphism restriction applies only to top-level bindings that look like they do not have any arguments. It also applies only to top-level bindings that look without, like they don't have arguments, that do not have an explicitly given type signature. As soon as we give a type signature, as we can see here as well, the monomorphism restriction does not apply. Now, what does the monomorphism restriction do? The monomorphism restriction says that a binding that satisfies these conditions, top level, looks like it doesn't have any arguments, does not have an explicit type signature, cannot have an overloaded type. And you can see that equal to itself and minimal naturally would have overloaded types. And that is exactly the situation that GHC is now running into, right? We are in a situation here where we have a top-level binding. It looks like it doesn't have any arguments, and there is an inferred constraint. And now GHC is forced to somehow resolve this constraint by the monomorphism restriction, because the monomorphism restriction says under these conditions, the binding cannot be given an overloaded type. So the inferred type, EQ A double arrow A to bool, is suddenly ruled out by the monomorphism restriction. And now, what can it do? Right? It could make a more or less random choice. Right? It could just choose an instance of EQ, or it can report an error that it cannot resolve the ambiguity. And in this particular case, it chooses to report an error, and that's the error message that we get. Right? That's the error message about the ambiguous type variable that we get. It comes from the monomorphism restriction. Now, it would be nice if GHC actually told us that this is what's happening, that the monomorphism restriction is being used. Unfortunately, that's not the case. You can see the word monomorphism restriction in here, but it's only coming from the fact that I call the module like this based on the video that I was going to be recording. So the file name mentions this, but otherwise we don't get a very useful hint here. Right? There are ways around the monomorphism restriction. So the best way around it in practice, I think, is to give an explicit type signature. The moment you give an explicit type signature to a function, and you start with a type signature, as I generally suggest anyway, you don't have a problem, because for bindings with explicit type signatures, the monomorphism restriction does not apply. So that is the best option. Okay. Another option is to explicitly disable the monomorphism restriction. And you can do that by means of a language extension. We have seen these language flags already. And then you would have to say no monomorphism restriction up here. Oops. I somehow misspelled it. Oh yes. No monomorphism restriction. And if I do this, I can get rid of these type signatures and everything's fine, right? I get the exact infer types as I probably would have expected them. Now, you might ask why, right? Why would someone invent something like this in the first place? Why would the language designers have come up with a monomorphism restriction? And certainly this has been a controversial topic among the Haskell designers over the years. I mean, this has been discussed a number of times. And the reason is, however, there is a reason. The reason is that if you look at the implementation of type classes, right, these class constraints in the general form, they turn into extra function arguments in the runtime representation. So if a function is overloaded, then it will typically be translated into a function that expects an extra argument. And that argument is often called a dictionary argument, and that dictionary argument is explicitly passing the implementation for the interface that we're asking for into the function. So for example, in the translation of equal to itself, the function would get an extra argument that explains to the function how to compute equality on values of type A, so that the moment this function invokes equality, it can select that implementation from the dictionary that it has been passed. Now, in general, you would expect that if you define a top-level constant binding, something like f equals hello, right, and that is a binding of type string, that you do not pay for this value more than once. That even if you now suddenly say you compute this value somewhat, you compute reverse of hello here, that you do not pay for the call of reverse to hello more than once. That because it's a constant string in the end, that this is computed once and shared throughout the program. Even though we have lazy evaluation in Haskell, this is typically an assumption that we can safely make, that bindings that we have are evaluated only at most once, right? They are not evaluated before they are even needed, but they are still shared among all their users. And if this is a top-level constant, we may expect it to be shared throughout our program and thus not paying multiple times. Okay, but now if we suddenly have a class constraint on this, now it's really just a string, but if we have a class constraint, such as an EQA constraint on this, right, then all of a sudden, this turns into a function, even though it looks like a constant. And functions have to be re-evaluated every time, because every time you call them, the argument could be different, and you have to evaluate given the argument. And even if the argument isn't different, Haskell does not have an automatic way in which it somehow memorizes the function arguments that have already been passed and tries to be clever about it. So the moment there is a class constraint, the result is effectively no longer shared and recomputed every time. And because if you write something that looks like it doesn't have any arguments, and you don't give an explicit type signature, because this fact of whether it is actually going to be shared or not is actually rather subtle, right? It depends on the infer type, whether it has a class constraint or not, because this can be leading to misleading assumptions about the complexity as well. That is the original motivation for the monomorphism restriction. Now, personally, I think this is probably not ideal. I mean, I would rather have turned this into a warning to say, like, oh, you have a top-level binding with an overloaded type. You might want to give it an explicit type signature or explicitly make it monomorphic, right? But turn that into a warning rather than just change the infer type. But nevertheless, that is there is a real trade-off here, and you can, in the best way, I think, work around it just by being explicit and by giving an explicit type signature. So I think that is the best option. Not to disable the monomorphism restriction completely, although that may also be a viable option. And certainly in some, like if you're developing an application and you're agreeing that you should never rely on the monomorphism restriction, then disabling the monomorphism restriction for the realm of your particular application may be fine. To give another example where this also occurs, let's take this out for the time being again, right? And let's actually put back in the type signatures that we wanted in these two cases. So here we still don't need it even without the monomorphism restriction, because there's really no class constraint involved in this example. Right, but another example where this applies, but is observed in a slightly different way, is if we make a binding such as x equals 42. Here we suddenly get x : integer as the suggested type. So we don't get an error message, but we nevertheless get an unexpected behavior, because if we ask what is the type of 42, we of course get that it is an overloaded number literal, right? But suddenly after binding it to x, the suggested type is integer, and we're seeing that there is defaulting taking place, defaulting the following constraints to the type integer. So the num constraint gets defaulted. Why is this? Well, again, this is for the same reason, just the consequence is slightly different. Right? The monomorphism restriction applies to x because it's a binding which looks like it doesn't have any arguments, and it appears without an explicit type signature, so it cannot have an overloaded type. But for numeric classes, GHC, even GHC, which is more reluctant to default than GHCi, is applying defaulting. And I mentioned before that preferably it will then default to integer if it can. And if it cannot use integer because that type does not apply, so for example, if we write 42.5, then it cannot, gets a fractional constraint, it cannot be defaulted to integer, then it will default to double, as we can see here. So here this is still the monomorphism restriction that is in place, but it is combined with defaulting. And so rather than an error message, we now get a defaulted situation. But again, perhaps in this situation, the motivation for the monomorphism restriction is a little bit more obvious, because really you would not expect 42 to always be the result of a function call every time you use it now. So if you use x at the type and you actually say x has the type num a double arrow a, then at runtime this behaves like a function, because we don't know, we don't have a concrete representation of 42 yet. We have to check in the dictionary for the num class how the 42 is actually supposed to be interpreted. and call the from integer function in the num class in order to actually get to the concrete representation for the particular type. We would probably not expect, if we just had x equals 42 there, that it's not just a shared constant that we can use over and over again, right? So you can see that there is a certain reasoning behind the presence of the monomorphism restriction. If you explicitly give it this type signature, then you're kind of warned. That's why it's a good idea. And otherwise you can make a specific choice, right? And that is also fine. You can yourself explicitly say that you want this to be of type int or you want this to be of type integer. But it is something to keep in mind. Okay. Now, about the defaulting, what is exactly the rule again for defaulting? So GHCi will default ambiguous constraints, right? Either forced through the monomorphism restriction or because they appear somewhere in the middle of an evaluation where they are no longer part of the type signature and they can no longer be effectively selected by the user. Then GHCi will default such constraints if they involve a numeric class. So essentially something like num or integral or fractional. And then it will default, as I said, preferably to integer or subsequently to double. And there is actually a little known top-level declaration you can make in a Haskell module to tweak this behavior. So for example, you can change the default behavior roughly corresponds to this declaration that you can make in your module. That basically says, I want to preferably default to integer, and if integer does not apply, then I want to default to double. But I could do it differently. I could import data.ratio. I could say I want to preferably default to int, and if that doesn't work, I want to default to rational. And then you can suddenly see that the type that is inferred for x now changes to rational, and if I remove the .5, it changes to int. You can also say I only want to default to rational, always. Then you'll get rational even for something that looks like an integer. You can also say I only want to default to int, right? And not have rational as an option. And if I then write 42.5, we get an ambiguous type variable. Then, like in this case, defaulting does not work. The monomorphism restriction does still apply, right? And we get an error message about an ambiguous type variable anymore. And we can disable defaulting completely, which is perhaps the best use of the default statement, by just putting an empty list of types there, and then we'll always get an error. So the default declaration is very, very rarely used, and I think in general you should probably just not use it, because the point is that defaulting should be used with caution in the first place. It is a warning, so if you are striving for your code to be warning free, which most people do, you should always resolve defaulting by giving an explicit type annotation anyway. It may be useful to sometimes remove defaulting completely in order to not even get into that situation where you get the warning. Then again, often defaulting does kind of do the right thing. It's not too bad. So it's a bit of a trade-off. But nevertheless, you know now what the rule is. So GHCi will basically only do this for numeric classes. So if we have a situation where numeric classes are not involved, and I had this contrived example before, strange where I had a function from string to string, where I was trying to show something that is first read. Right, here we have an intermediate type, the type that we parse the value at, that is then immediately shown again. It does not appear in the outer type signature, so it's completely ambiguous because we don't have anything. So we get an ambiguous type variable error message. And regardless of the defaulting rules in place, we do not get any defaulting happening here because there is no numeric class involved in all this. If we suddenly make a numeric class be involved in all this, right? Oh no, this is wrong. Sorry, I did it on the wrong point because x is a string, right? But if I say read x plus 1, then, right, the intermediate type suddenly is a member of a numeric class, and we suddenly get defaulting again to integer, right? Happening to integer. So that's the rule for GHC. The rule for GHCi is a bit different, because as we had seen that if we do the same thing within GHCi, right, we actually get it accepted, but now it's also defaulted, and if I want to see the warning in GHCi, I can see that GHCi is defaulting the constraint to the unit type. So GHCi is much more eager to default, and GHCi will additionally default preferably to the unit type. So these are additional rules. And you can change this behavior as well in both directions. So there is again a language extension in GHC that states whether these extended defaulting rules should be used or not. And you can enable these extended defaulting rules by another language flag. That is called extended default rules, I think. And now if I remove the +1 here and I look at the warnings, I'll see that I get the defaulting to the unit type here in GHC as well. Similarly, I can actually, with this notation set -x no extended default rules, I can also disable the extended default rules behavior from a GHCi, and suddenly I'm getting an error message about an ambiguous type variable in a situation like this. Again, we can ask a little bit about the motivation. Why did the designers of GHC or Haskell decide to make this difference between GHC and GHCi? The reason for this is primarily something like the empty list. If I type the empty list now that I've disabled the extended defaulting rules, right, I suddenly get not the empty list printed back as we're used to, but I get an ambiguous type variable arising from a use of print. So let's think again what GHC does when we enter an expression. It is evaluating the expression and trying to print the result back to us. And in order to print the expression, a show constraint has to be resolved. And so if we actually look at the command that GHC executes, it's this print empty list constraint, and I'm slightly confused that I cannot even ask for the type signature of this now. That's a little bit confusing. Why can I not even ask for the type signature of this? This is a little bit strange. I'm actually a little bit surprised here, but in principle, right, the type of show of the empty list has the show A constraint. So what I would expect to see is that the type of show of the empty list is show A. Oh, right, because the end result is a string, and I think the rule is that such a type is considered an ambiguous type already. So because we have a constraint on a type variable that doesn't actually appear in the type signature, right? The result of showing the empty list is a plain string, but we have to resolve the show A constraint. And that is inherently ambiguous. I think that's why we get the error message, even if I just ask for the inferred type. We would get something like this. Or similarly, if I call print of the empty list, the situation is similar, right? So even though the element type of the list ultimately does not seem to matter, right? We have to make a choice for it. We have to make a choice for it in order to resolve this constraint. And there is no contextual information here to resolve this constraint. So normally, now with the extended default rules being active, GHC just defaults this to unit and does resolve the constraint that way. And then we can type in the empty list and get the empty list printed back. But if we disable this, right, then it is ambiguous, and then we get an error message. And curiously, it does actually matter. I said it does not seem to matter, but it does matter, because if we give an explicit annotation that we want to treat this as a list of integers, then it's fine, and we get the empty list printed back as we would expect. Or as a list of units, then it's fine, we get it printed back as we would expect. But if we say we want to interpret this as a list of characters, that is a string, then the special definition of showing for lists for strings kicks in, and it actually prints this between double quotes as an empty string. So it does matter, right? And it is somewhat premature to jump to the conclusion that if we just type the empty list, that we meant the empty list at a type that isn't a list of characters. So, right, there is an argument to be made. But of course, I mean, the empty list, being able to type in the empty list into GHCi and get a result back is very useful. Similarly, right, even for normal defaulting, being able to make calculations such as 2 + 2 is very useful, but it involves defaulting, right? And that's why that sort of stuff is even enabled in GHC. But again, it would be much less convenient to work with GHC. Whenever we do any sort of numeric computation, we would have to annotate their types, because very often the result type is actually overloaded, and defaulting is going on there almost all the time. Okay, so this is nearly the end of this video. I just wanted to briefly mention this any type that we have been seeing a number of times. There is not all that much to say about this one. It is essentially just a helper that GHC sometimes uses in order to continue type checking. So because we want to have as many type errors about a program as possible, right? I mean, if we have a large program and we always stop at the first error that is slightly unsatisfactory, and then for type checking, GHC tries to recover from errors and go on and then report a whole bunch of errors. So whenever there is an error somewhere, GHC will then assume that thing has the type any, and continue type checking in the rest. And then more errors may arise. So any is essentially just an internal helper type that is rarely ever used in an actual program, and it has a little bit of a special role as behaves a bit like a type variable that you can instantiate to anything, only that it is a concrete type that you can basically use as anything. But it is more or less an artifact here of the type inference process, and you almost always see it in connection with errors. So if you see the any type arising, then most likely there is an error close by, and the error is what you should fix. So it's not the real type of this minimal binding here, right? But that's how the presence of any can be explained. Okay, so let's summarize once more. Right? The monomorphism restriction is something you may run into occasionally. I think the best way around it is just to train yourself to always give type signatures. If you give explicit type signatures for your bindings, then you don't run into the monomorphism restriction. If you forget giving a type signature and you get some strange behavior anyway, right, then the monomorphism restriction means that you unfortunately cannot just trust the inferred type here. You cannot, I cannot now just click on this and get the proper type. I have to kind of do this manually. I mean, either I have to just remember what the type is, or I have to use this in GHCi and then copy the bounded A, double arrow A manually in here as the type signature. But giving the explicit type signature will always fix it. Right? So that's the best way around it. You can also work around it by disabling it, but that should probably be a project-wide agreement as to whether you want to do this or not. And defaulting, right, is there are these two levels of defaulting. There is defaulting as available in GHC, which only happens for numeric classes. There is defaulting as it happens in GHCi, which is happens to a wider range of classes. Both are useful up to an extent. I mean, primarily in GHCi, I think it is actually useful for convenience. Again, I think it is good in actual programs to enable all warnings. Then you're always being warned about defaulting going on in your program. And I think you should probably always consider it and make an explicit type annotation in such a case to either confirm that defaulting has made the right choice or correct the choice that defaulting has made and instead govern it towards whatever choice you would have made. And defaulting and the monomorphism restriction can interact in situations like this. Top-level bindings for numeric values, right? And again, also in a situation like this, where I've been writing y as a lambda abstraction, so it looks like it doesn't have any arguments, so it would have type num a to a, but because it does not look like it is a function and doesn't have an explicit type signature, monomorphism restriction applies here, and we get integer to integer. Okay, that's it. Hope I managed to perhaps reduce the confusion a bit rather than increase it. As I said, and you're not running into this stuff all that often, right? But when you do, you now know what the underlying concepts are.